All right, in this second example from Improper Integrals lesson, we're going to evaluate the improper integral from 1 to infinity, 1 over x squared with respect to x. So this one is one of the obvious ones that it's improper because your upper limit there is, in fact, infinity. Let's take a look at a graph here. So we're starting this little pink region here, and remember what we're going to do is we're going to get rid of that infinity. We're going to replace it with a b. You can see b is in the picture, and then take the limit as b goes to infinity and see if this approaches a particular number or if it's unbounded. So let's take a look at that one, huh? Okay, so again, what makes this thing improper is the fact that we've got an infinity right up here. It's very obvious. Right, and then we want to turn this thing into a limit. So I'm going to take that infinity out. I'm going to replace it with a b and take the limit as b goes to infinity. You don't have to use b. You can use whatever letter you want as long as it's not one that's already used in the problem. Definite integral from 1 to b, 1 over x squared dx. Now again, the whole reason why I do that is because now I'm going to assume that b is some sort of finite number, and then I can use the definition of a definite integral on it. I can use the fundamental theorem of calculus on it, and then once I get its antiderivative, then I can take the limit. We're going to do that part at the end. We're going to take the limit and see what happens as b goes to infinity here, right? So again, right now b is some sort of finite number, and we're going to see let's just find the area under the curve from 1 to b. And then when we're done, let's see what happens when b gets really, really big. All right, so I'm going to write this limit down again and take its antiderivative, but maybe it's helpful if we think of this thing as x to the negative 2 power. So power rule, that's what we're going to use on that. Add 1 to the exponent is going to be negative 1, and then divide by that new power. So it's going to be negative 1 over x, evaluated from 1 to b. And then use fundamental theorem of calculus on it because we're allowed to now. b goes to infinity, again, of negative 1 over b minus a negative, so plus 1 over 1. Okay, and now I can take the limit because the definite integral has disappeared. We've evaluated it now. So this first term, as b goes to infinity, I'm taking negative 1, dividing it by an increasingly larger number. That's going to go to 0. So this part right there is 0. And then it does not affect the 1. And the value of our limit is just equal to 1. And we're going to say then that this converges to 1. What that means is that as b gets bigger and bigger and bigger, our area is getting closer and closer to 1. It's converging to that particular number. So here's an example of an infinite, unbounded region that has a finite area. Okay, but that's kind of interesting. Like, let's compare that to the previous example that we just did. So we just evaluated the improper integral from 1 to infinity of 1 over x squared, and we saw that it converged. The previous example that had to do with that natural log, the 1 over x thing, it diverged. So let's take a look at the graphs of each of these. Here's the 1 over x, and let's compare it to 1 over x squared. What do you notice about these two things? Well, the one that's in the blue, the one that converged, it collapses down to the x-axis much, much faster than the 1 over x, the pink graph. And so it doesn't accumulate as much area as that 1 over x, the pink one, and so it converges. And that's one of the things that we can kind of look for to see if one of these things is going to converge. Does it get down to that x-axis quick enough? And if it does, it's going to converge. These two things are examples of what we're going to call p-series. P has to do with a power. It's not the same thing as a power series. It's called a p-series, just so that they don't get confused. And we're going to see them again when we do our series lesson. The p in this case, again, does refer to the power. On that first definite integral or improper integral, it's that power of 2 that's on the x. And on the other one, it's a power of 1. When that power is 2, it converged. When the power of 1, it absolutely does not converge. Okay, so we're going to summarize that like this. So if your p-value for your p-series is greater than 1, it's going to converge, and specifically it's going to converge to 1 over p minus 1. Now this little formula is only going to work if that lower bound's 1. If it's not, it still will converge, but perhaps to a different number there. You'd actually just have to work it out. Okay, so our previous example, our p-value was equal to a 2. 2 is greater than 1, so therefore this thing is going to converge. If I plug this into the little formula, it's 1 over 2 minus 1. 2 minus 1 is 1. 1 over 1 is 1. And that's exactly what we got for our answer. Okay, if your p-value, on the other hand, is less than or equal to 1, this thing is going to diverge. We saw the case where, in the pink graph there, p was equal to 1. It diverged. Anything less than that, it's also going to diverge. Think for a second if it was negative. If it was a negative number, then that exponent would actually shoot the x up to the top, and now you've got something that's just getting infinitely bigger and infinitely bigger, so that part should make some sort of sense. Okay, definitely make some sort of note about this, and I'm going to take a moment to actually derive this for you, to prove the convergence of this one right here, because it is pretty special, and it is something that we're going to see quite a bit whenever we do our series lesson. Okay, so coming down over here, let's prove the convergent one. So P series. All right, so in order for it to converge, our p-value has to be greater than 1. Okay, so we're going to say let p be greater than 1 for this improper integral from 1 to infinity, 1 over x to the p with respect to x. Okay, so I have myself an improper integral. As an improper integral, what I'm supposed to do is turn that thing into a limit. So I'm going to turn that into, I'm going to take away the infinity, replace it with a b. So limit b goes to infinity of the definite integral this time from 1 to b, 1 over x to the p. And then maybe I rewrite this so that it's a little bit easier to find the antiderivative of. And here's where people get lazy, like not wanting to have to write that limit down each time. So as long as you have it at the very beginning, you should be covered, and definitely get rid of the infinity and replace it with some kind of variable. It doesn't have to be a b, it's just as long as it's not the same thing as anything else in the problem. So 1 to b x to the negative p power. And then we can apply the power rule to, or the power rule of antiderivatives. We just add 1 to the exponent here. So we have the limit b goes to infinity again. X to the negative p, add 1 to the exponent over same exact exponent, evaluated from 1 to b. All right, so now I'm going to take a moment to actually rewrite this. The reason why I'm going to do that is because if I can make that a negative exponent, I mean, this is exactly what we did, let's say, back over here, that x still should have been down in the bottom. And that's what we're going to do on this example. And in order to do that, I need to factor out the x. I mean, factor out the negative. So on that particular part of it, think of this as negative. Factor out the negative sign, it's p minus 1. So I'm going to rewrite both the top and the bottom just like that. X to the negative parentheses p minus 1 over same thing, evaluated for 1 to b. Okay, again, I did that because now I've got myself a negative exponent, and that x can shoot down to the bottom. So I'm going to rewrite this yet again. And I'm going to take this as a coefficient, this negative 1 over p minus 1. I just leave that right up front. And then times 1 over x to the p minus 1 power. Still evaluated from 1 to b. Okay, so now we're ready to take the, use the fundamental theorem calculus on it and plug in our values. I'm going to leave this negative 1 over p minus 1 just right up front, okay? And then evaluate the part, the variable part. Now, as far as this goes, like, where am I going to put the b and the 1? Do they go into x's? Do they go into p's? Well, the p would have been some sort of set value for me. It would have been a 2 or a 3 or something like that. It's only going to go in for the x. So this should be 1 over b raised to the p minus 1 power minus 1 over 1 to the p minus 1 power. All right, and now we're almost there. So this part, of course, that's just 1, right? Because p to the, I don't even care what power, it should just be 1. That's some sort of finite value, so it's just 1. All right, and then over here on the right-hand, or the left-hand side, maybe I color this one in blue. This one here, as b goes to infinity, this number on the bottom's getting infinitely big, the top's staying 1, that's getting closer to 0. So then this evaluates to, without the limit, negative 1 over p minus 1 times 0 minus 1. 0's gone, who even cares about that? And I have this times a negative 1, which puts us at 1 over p minus 1, which is, I do believe, exactly what we said right up here in blue. Okay? All right, so let's talk about this in a little bit more detail here. So first of all, if if our p-value was, we assumed that it was greater than 1. Well, what if it was equal to 1? If it was equal to 1, we've already done that one. We've already done that one right up here, maybe. Where the heck was it? It's right here that we showed that it was infinite. So that case is covered. And then the second case is whenever it is, say, less than 1. All right, so if it is less than 1, let's take a look at this part here. Let me choose another color, maybe purple. All right, if your p-value is less than 1, p is less than 1, then that means that this exponent is going to be overall some sort of negative. If your exponent is negative, it's going to shoot the x value back up to the top, and then whenever you plug in your b going to infinity, that's going to get bigger and bigger and bigger, and this thing is going to be unbounded. So the only case for which this thing converges is when p is greater than 1. Okay. All right, so that concludes this video showing you when these p series converges to 1 over p minus 1 as long as p is greater than 1.